Okay, so welcome everyone to Guided Study Group, week 10 of Math 140. And so last week we started the first piece of materials for the final exam, which is antiderivative and the general concept of integral. This week we're going to work more on the fundamental theorem of calculus and some of the basic technique to find integral. So the fundamental theorem of calculus say, suppose f is continuous on a closed interval from a to b. Then if you have gx equal to the integral from a to x of ft dt with x bounded from a to b, then g prime of x is going to be fx. G prime is going to be fx, and g is going to be continuous on the on the closed interval from a to b and differentiable on the open interval from a to b. We also have the concept of the definite integral with the bound of fx dx from x equal to a to x equal to b is equal to big F b minus big F a, which we learned last week. F be the most general antiderivative or any antiderivative of f. That is a function big F such that big F prime is going to be small f. Some of the problems that you might be asked in this sections is that you might be given gx or the integral from a to u of x ft dt. Would u be any kind of function of x? Find g prime of x or d over or the derivative with respect to x of that integral. And so we're going to see that in the first example. We can also be asked to evaluate the definite integral from a to b of fx dx or related word problems. And so this part is not only the main focus right now, but it's going to be the focus of Math 140, at least during the first midterms. So make sure that you work well on this, and if you don't, try to do a lot of practice, and as well email me anytime if you have any questions. The first example is question 14 of section 4.3 in the book. Find the derivative of hx, which hx be the integral from 1 to square root of x, z squared over z fourth plus 1 dz. And so for this one, we're going to use the fundamental theorem of calculus to solve this one. We have the fundamental theorem of calculus say, if you have gx be the integral of ft dt from a to x, then g prime x is going to be fx. So what we need to find here is that we need to find h prime x. Well, at first, when looking at the fundamental theorem of calculus and going to these questions, a lot of people make a mistake thinking that it's h prime of x is just going to be as simple as plugging square root of x into this, which you're going to have x over x squared plus 1. But that's not right, because the boundary here is not x. If it's x, you can immediately just substitute it in, and it's going to give you whatever the answer is. But in this case, this is not x. So we have to do that extra step based on the fundamental theorem of calculus, is that we have to find d dx of 1 to square root of x z squared over z fourth plus 1 dz. Or we can rewrite this one as d over d square root of z 1 square root. Well, we can have z squared dz multiply d of square root of z with respect to x. And so in this case, then here you can simply just plug square root of x in, because now it's the derivative with respect to square root of x based on the boundary, based on the integral of square root of x. So this one is just going to be equal x squared plus 1. However, this integral, the extra part, I'll give it another color, is the derivative of square root of x with respect to x, and we have to multiply this part. Is because the boundary over here is not square root of x, so you have to account for that when you take the derivative of the entire integral. So this is You're gonna learn this later when we go to the next section, which we call is the chain rule of taking derivative of an integral. And so this one we have is gonna be 1 over 2 square root of x here. And so if you canceling out, kind of like simplifying the algebra, this is what you're gonna end up with. So this is the final answer, and not just simply just plug in square root of x into the questions, as a lot of people might have thought when they see the fundamental theorem of calculus. Now let's work on example 2, question 28 of the section 4.3. This one say evaluate the integral from 0 to 4 of 4 minus t multiply square root of t dt. And this one is going to base on what we learned last week. So last week we learned how to take the antiderivative of some of the general functions and some of the commonly seen functions like polynomial. And so we have this formula, hopefully that you guys still remember, is that the integral of x to the n dx is going to be x to the n plus 1 divided by n plus 1 plus c. And that is the formula of the most general antiderivative of the polynomial x to the n. And so in this case, based on the second point of the fundamental theorem of calculus, we have to find what is one of the antiderivative of f, which is big F, and then plug in big F of b and minus big F of a. And so let's find the most general antiderivative first. We're gonna rewrite this as 4 square root of t minus t square root of t dt. And so that's we have 4t to the half minus t to the 3 half dt, which is going to give us 4 multiply 3 over 2 t to the 3 over 2 minus t to the 5 over 2 divided by 5 over 2 plus c. And this one we have is that 8 over 3 t to the 3 over 2 minus 2 over 5 t to the 5 over 2 plus c. And so when we plug in for big F of b and big F of, so this one is what we call the function big F. But when we plug in, we can completely ignore this c, because essentially these two constants, say if you plug in f of b, you have some number, and then you have plus c. And then when you plug in f of a, say here is a and b is 4 and 0, you're gonna have something plus c again. And so when you subtract one from another, you can essentially cancel this c out, so you don't need to worry about it too much. Now in this case, I will just plug in 0 to 4, 4 minus t square root of t dt. And in this case, I'm just gonna plug in, and this is how I'm gonna denote that mathematically if you guys ever need to plug it in. 0, 4. And first you're gonna plug in 4, the upper boundary first and then the lower boundary. So you have a over 3 2 to the third, because square root of 4 is 2, and then 2 to the third. Okay, so you plug in, and then so square root of 4, so here is basically just 4 to the 3 half, which is going to be just square root of 4 to the third, so it's going to be 2/3 minus 2 over 5, 2 to the 5th, and then 0 and 0 is just going to be 0. So if you do the algebra, I guess what you end up having is that it's going to be 128 over 15. So that's my answer for this questions. Again, the step is just first find the most general antiderivative based on what we learned last week and what we've learned so far until now, and then plug in the two ends, upper boundary first and then lower boundary. Next one is question 57 of this session in the book. Let big Fx be the integral from pi to x of cosine t over t dt. Find the equation of a tangent line to the curve at that point. First of all, I always ask you guys, what is the most general form of the tangent line of a curve at a single point? So it's going to be y equal y prime at x0, x minus x0 plus y0. Would x0 be the x coordinate at that point? And here x0 is equal to pi. Now, first we need to find what is f prime of x first. And based on the fundamental theorem of calculus, we can immediately say it's going to be cosine of x divided by x. Why? Because here, when you have x as above upper boundary, it doesn't really matter what is the lower boundary, but you can immediately conclude that based on the fundamental theorem calculus, f prime of x is going to be cosine of x divided by x. And if you plug in pi, f prime of pi is going to be negative 1 over pi. Therefore, you have the tangent will become y equal negative 1 over pi, x minus pi, and we also need to find f of pi as well. So if you plug in here, f of pi is going to be, oh, not here, sorry. It's going to be the integral from pi to pi of cosine t dt. And as we mentioned last week, antiderivative, when we take it, that is basically the area under the curve. And so if you have the area under just one single point from pi to pi, the area is 0 because it's essentially just a line and it doesn't have an area, so it's 0. Therefore, we have is 0, and so our tangent equation is going to be negative 1 over pi multiply x plus 1, and that is the equation of our tangent line. So the challenging part here is know how to apply the fundamental theorem of calculus and what we learned last week, the definite integral of any function from a to a is 0. That's one of the properties that we learned at the end of last week. Now we're going to go to the two next sections of this week, which is 4.4 and 4.5, indefinite integrals and substitution rule. So indefinite integral, as I briefly mentioned last week, is the integral without the numerical boundaries in the integral. So, and the resulting outcome that we're looking for is a function, big F of x, and not any single number. So this is a big note that I make over here. The indefinite integral of fx dx is a function, but the definite integral with the boundaries from a to b of fx dx is a number. And so, again, I mentioned the table of some indefinite integrals that we talked about at the end of last week, and with some extra that I mentioned here, secant square, cosecant square, secant tangent, cosecant cotangent. For now, they're not that really important, but just make sure that you're aware of them and kind of like know where you should look them up, at least until the exam, where you should know and remember all of them. In the next class, 141, you're going to see these 4 trigonometric integral a lot in the first midterm at least. Then we have 4.5, substitution rule. So this is kind of like your first actual technique to take integral in this class. We're going to learn much more, like 5 or 6 more techniques in 141 later. But substitution rule is like the basic of all of them, the most basic among all of them. So if you have u is any function of x, gx, it's a differentiable function whose range is an interval I, then f is continuous on I. So it's continuous on the range of g. And then you have the integral of f of gx multiply g prime of x dx is equal to the integral of fu du. And so what's the point of doing this? Usually your integral is going to be in the form of, say, 1 over x to the 4th plus 1, or something like x squared over x to the 4th plus 1, x plus maybe 2 here plus 2x plus 3, things like that. And these are not that easy, but when you substitute something, say put this as u and you take du, then essentially you're gonna make the integral simpler by a change of variables. And so it's just one of the techniques that make your integral easier, simpler, and much better to solve. So some of the problems is try to apply this u substitution into finding integral of complex functions. First of all, you need to know how to choose u and take the derivative of that. Du be something of gx, maybe some functions, and express the integral in u only. So you cannot take integrals when your integrals have two variables x and u at the same time. So before you can actually do any more things about the integral, make sure that you put them all in one variable. Then take the integral with respect to u. And finally, when you already get rid of that integral sign, you return that into the form of x based on our initial substitution. Let's do some of the example later to see that. We also have some other theorem saying if you have g prime is continuous on the closed interval from a to b, and if f is continuous on the range of gx, so it's continuous on the range of ga to gb, then you have that integral is equal to this. So this is where you have the change of boundaries as well. Earlier we have only indefinite integral, so we don't really need to care about boundaries. But if you have definite integral, essentially what you end up with is a number. So if you don't change your boundaries when you change the variable at the same time, then you have x b a b, u is going to be g a g b. If you don't change your boundaries, your final answer is going to be wrong, because the boundaries that you apply after you finish taking the integral in the form of u is no longer applicable for that boundaries, which is initially given in the form of x. We also have some kind of like theorem about integrals of symmetric functions. So say if f is even, and we can check for that when you take f of negative x. If it's equal to fx, then the integral from negative a to a of fx dx is going to be twice the integral from 0 to a of fx dx. Similarly, for f is odd, and we can check it by taking f of negative x. If it's equal to negative of fx, then you have the integral from negative a to a of fx dx is going to be 0. And so this is the two things that sometimes can be really helpful when you look at the functions and you really have no idea how to solve it. But if you can use one of these two, say if you can prove that it is an odd function, you can actually simplify and conclude that it's equal to 0 sometimes. Especially when you have the hint be the boundary. So say if you see the boundaries be like from negative a to a, that's one of the hints that you might have to use even an odd function to solve it. Now let's work on the example 4, which is question 15 of section 4.4. Find the general indefinite integrals of this expression. And so we have 1 minus sine cube t divided by sine square t dt. And note the fact that this is indefinite integral. So what you end up having, it should be a function of t and not a number. And so this is one of the techniques that algebra wise I want to show you guys in this example as well, which can be really helpful in your in Math 141. So in this case, when you look at it and you don't know if you can use any of the integrals that you already learned, say in that table, but you know the fact that these are the trig integrals that you already know, therefore maybe try to think about maybe making them into one of these forms. And so to do that, first of all, I will split this fraction into two individual fractions. So what I am having is that I will have cosecant square t minus sine t dt. And so we already know what is the integral of cosecant square and what is the integral of negative sine t. So we can immediately use the table to solve that. A lot of students usually ask me like, how do you know that you're going to break them out and then, you know, divided them to put it in the form of cosecant and sine? I would say it comes a lot from practice And with your current knowledge, where you haven't known a lot of techniques to take integral, you should try to find ways to apply the basic integrals that you already given in maybe the table and in the book. Try not to like think of something super complicated. It might be something that very simple in front of you, but you have to do some algebra to finally arrive to that form. So the integral of cosecant square is cotangent t. Is it cotangent or is it negative cotangent? Negative cotangent. So negative cotangent plus cosecant. No, plus cosine t, and then plus c because it's a function and you want it into the most general form. So you have to add a plus c with c be any constant. And so that's my final answer here. Let's go to the next one. Evaluate the indefinite integral in this form. And so in this case, when you look at the general form of integral, you don't have anything that can be applicable for this, because even when you break them out, you have a over the square root and then bx squared over that square root, and it's not leading you anywhere. So this is where comes the technique, and in this case we're going to use substitution. So in this case, there are two ways that you can use. You can either substitute u be 3ax plus bx cubed, or you can substitute u be 3ax, square root of 3ax plus bx cubed. I'll do the first one, but you guys please feel free to try the second way to substitute in, because there can be more than one way, and one way can be just like slightly shorter than another. As I say, the next step is to take what is du. So this is just a polynomial of x and to the square root. So we're gonna first take the square root out. You have 3ax plus bx cubed to the negative half, multiply 3a plus 3bx squared dx. Always remember the dx. And so you can take the 3 out of here. So 3 over 2 square root of 3ax plus bx cubed. And then we have a plus bx squared dx. And so in this case, it can immediately give us almost like the expression that we have. So if we just do some algebra manipulation, this is what we're gonna have. So we have this one is gonna be a plus bx squared over square root of 3ax plus bx cubed dx. And so now we already have the entire integral. So 2 over 3 du is going to be 2 over 3u plus c. That's the most general form of integral, but then it's in the form of u, and so we have to follow the last step that we have, which is put it back in the form of x. So just put whatever u in to this expression plus c, and that is my final answer for this. You should get the same answer using the second substitution. It can be slightly longer, but then again, it's gonna give you the same answer. And as I say, I've tried both of them. So one is just like 1 or 2 lines longer than another. This is the shorter one, but it's usually harder to see. So it's up to you and how much you do the practice to actually see these points. Again, if you have any questions, please feel free to email me during the week. I try to put this one up early so that you guys can have a look at that and email me with questions. Now it's example 6, which is also the last example. Question 51 of section 4.5. Evaluate the definite integral from 0 to 1 dx over 1 plus square root of x to the 4th. Now, we can try using u substitution, because again, when I look back at the basic integral, I don't have any idea how to do it, and so I'm going to use u substitution. U plus square root of x. So I have du is going to be 1 over 2 square root of x dx. Now, this is hard to eliminate and put everything in the form of u, because here, if you look at dx over that, so you have dx is going to be, basically you're going to substitute dx with something related to du. We have 2 square root of x du, right? And so you have 2 square root of x du with the integral on u fourth. Now you have to get rid of the square root of x and represent it in the form of u. You don't have any idea from du, but let's look it back here. You can substitute square root of x be u minus 1. Then it's still in the form of u, right? So you have 2u minus 1 du. And so it allows us to do the step that we have in our procedures. Now let's do the change of variables because this is the definite integral. So you go from x to u, 0 to 1. It's going to go from 1 plus square root of x. U is going to be 1 and 2. So here the integral is going to become 1 to 2, 2u minus 1 du, u to the fourth. And now we can do the separate of fraction again to make it easier to use the x to the n integral is equal x to the m plus 1 over m plus 1 plus c. This is dx. So we have 1 to 2, 2 over u cubed minus 1 over u fourth du. Or you can rewrite this one at 1 to 2, u to the 2u to the negative 3 minus u to the negative 4 du. And what we end up having is that 2 outside, negative u to the negative 2 plus 3 to the plus 1 over 3 u to the negative 3 from 1 to 2. And so again, I told you not to bother about plus c part here. So you're going to have 2 negative 1 over 2 square plus 1/3 1 over 2 cube. And do the same thing for minus, and minus is a plus 1 over 1. Minus with a plus is a minus 1 over. And so in this case, if you do the algebra, I would say what you end up having is going to be 1 over 6. And so the important part here is to know the fact that you're going to use substitution and do this tricky part of transforming square root of x into the form of only u. And then again, we're going to do the fractions, and it's going to come a lot from your practice. Now, if you don't have any more questions, or you want to send me questions through email, please do that. If not, if you don't have any other troubles, I'll end the sessions here. Try to do all the practice problems that Dr. Kasha gave on Canvas and in the book. And if you need more practice, let me know. I'll send you practice if I have them. Other than that, I'll see you guys next week. Have a great week, and I look forward to your questions and emails.